So today we will discuss separable Hilbert spaces. Okay, and we'll see that there are only two separable Hilbert spaces. Okay, one is finite, and the infinite is only one. That's L2. L2 is the only infinite separable Hilbert space that we'll discuss in this theorem. So let's state this theorem. एंड फाइनाइट में भी वही होगा ना, एल टू एन होगा, क्योंकि वहाँ पर हमने फाइनाइट केसेस में हमने जो है ना जनरल डिस्कशन फाइनाइट डायमेंशनल में हमने एल पी एन को डिस्कस किया, एन डायमेंशनल जिसमें पी एफ नॉर्म हमने डिफाइन किया था, नॉर्म ऑफ एक्स वेयर एक्स इज एन टपल, हमने इसको ऐसे डिफाइन किया था, अगर आपको याद होगा इट्स पी होल पावर 1 by p. So this is irons from 1 to n. Okay, so this is LPN. LPN means set of all n tuples having this norm, pf norm. तो हमने ये चेक किया था L2n जो है ना, दिस इज द ओनली इनर प्रोडक्ट स्पेस, और ये हिल्बर्ट स्पेस भी है. ठीक है, और हम प्रूव करेंगे ये जो फाइनाइट डायमेंशन हिल्बर्ट स्पेस होगा ये सिर्फ एक ही होगा, दैट्स L2n, ओनली वन फाइनाइट डायमेंशन हिल्बर्ट स्पेस. इसी तरह से आपने LP को डिस्कस किया. LP मीन सेट ऑफ ऑल सीक्वेंसेस pf पावर समीकरण. ओके, सो इसमें भी नॉर्म इसी तरह से, बट वी हैव एन इन्फिनाइट, we have a series here. It is I runs from 1 to infinity mod of xi power p whole power 1 over p. So with this norm, okay, LP, the set of all sequences with this norm, pth summable sequences, pth power summable. So we have seen that only L2 is Hilbert space. L जितने भी ये LPs हैं 1 lesser equal to p less than infinity, or in fact equal to infinity b, तो सिर्फ इनमें सिर्फ L2 हिल्बर्ट स्पेस है. और अब हम प्रूव करेंगे जो भी इन्फिनाइट डायमेंशनल हिल्बर्ट स्पेस होगा और सेपरेबल भी होगा, सेपरेबल एंड इन्फिनाइट डायमेंशनल, वो सिर्फ L2 होगा, वो हम इस थ्योरम में डिस्कस करेंगे. सो लेट्स स्टेट दिस थ्योरम. लेट H be a non-zero Hilbert space. Let H be a non-zero Hilbert space H be a non-zero Hilbert space over some field K, where K is either complex or real. Then the following conditions are equivalent, or following statements are equivalent, then the following conditions are equivalent. So number 1 is H has countable orthonormal basis. H has countable orthonormal basis. Second, H is linearly isometric to H is linearly isometric to which space Kn, or you can say L2n, क्योंकि L2 हम n को हमने डिस्कस किया था, L2n. Okay, let's write here Kn. Kn is fine. Okay, ऊपर हमने फील्ड लिखा है और फील्ड K, so it's better to write here Kn for some n. So means it is fine. In case it is finite dimensional. Okay, for some n, or it's isometric to L2. या तो ये Kn होगा finite dimensional, अगर finite dimensional नहीं होगा, if it is infinite, then it will be isometric to L2. Okay. Third, H is separable. H is separable. So this is for Hilbert space, not for inner product space. So because we have this inner product space, we have C, A, B, okay, with respect to the integral inner product integral norm. It's an inner product space, but it's separable, and I think it may not be. It's not isometric to L2 because because L2 is Hilbert and CAB is not Hilbert. It's inner product space. Okay, so so far this is separable inner product space, but it's not isometric to L2. So this theorem is for Hilbert space actually. Note this point. Proof. So let's see, 1 implies 2. So we have take this countable orthonormal basis. So let's take countable orthonormal basis. So that means we can enumerate those bases, orthonormal bases. That u1, u2 be a countable orthonormal basis. This set may be finite, huh? This may be finite. So based on this basis set, what we do, we define a map. So define for each x in H. Okay, orthonormal basis of H आप लिख दीजिए. Okay, of Hilbert space H. Okay, for each x in H, let's take fx equal to fx. It's a tuple here. जिसमें स्केलर्स क्या है? फर्स्ट स्केलर इसमें है इनर प्रोडक्ट ऑफ x विद u1. इसका सेकंड स्केलर क्या है? इनर प्रोडक्ट x विद u2 एंड सो ऑन एंड सो फोर्थ. अब ये डिपेंड है इस पर, अगर ये सेट फाइनाइट है, अगर इसमें n एलिमेंट्स है इस ऑर्थोनॉर्मल बेसिस का जो सेट है, इफ इट इज कंसिस्टिंग ऑफ n, क्योंकि काउंटेबल मीन्स फाइनाइट और काउंटेबल इनफाइनाइट. So in case it is finite, then obviously this is an n tuple in that case. And these are the scalars, n tuples of the scalars. So it means that in that case this tuple, it belongs to Kn. So in that case this f is a map from H to Kn. And in case it's denumerable, it's countably infinite, then we can see that the sum of the squares of these mod of the squares of these entries is finite. So in that case this will be a sequence, and this sequence will belong to L2. It's L2 sequence, means it is square summable. So we'll discuss both the cases here. So first case, if it is finite, okay, if it is finite, if u1 u2 is finite, is a finite set. Suppose say it's equal to this set u1 u2 up to un. Okay, then f जो है capital F, it's obviously a linear map. Then f is a map from H to K. Okay, H to Kn, right? Okay, and let's check that this f is linear. This f is linear. It's very simple. F is linear. How do we do that? Let's take any two vectors here and let x y belongs to H, and let's take alpha in the scalar field K. Then we see this f of alpha x plus y. So alpha x plus y, it's obviously in the H. So this is here inner product. x की जगह पर यहाँ पर है अल्फा x प्लस वाई, inner product of alpha x plus y with u1. Then second entry of this tuple is inner product of alpha x plus y with u2, and the nth entry of this tuple is inner product alpha x plus y with u2, right? So now you can apply the property, linearity property of this inner product. You can see this is equal to alpha times inner product x with u1 plus inner product y with u1. Then next is alpha times inner product x with u2 plus inner product of y with u2, and the nth entry is inner product alpha times inner product of x with un plus inner product of y with un. मैंने दोनों स्केलर मल्टीप्लिकेशन और एडिशन की दोनों प्रॉपर्टीज मैंने एक साथ अप्लाई की यहाँ पर, अब एक स्टेप मैंने स्किप कर दिया इसमें. So now you can again the component wise addition apply here, because this k is a field, okay. This k is a vector space with respect to the component wise addition and scalar multiplication. So you can see that this is equal to alpha times inner product x with u1 inner product x with u2 inner product x with un plus inner product y with u1 plus, sorry, it's here tuple now, second tuple, that's this inner product y with u2, then inner product y with un, and that's equal to alpha f of x plus f of y. Okay, so alpha is this f is linear. This f is linear. So also this kn, this, okay. So also this kn जो आपका स्पेस है kn, this kn, okay, what's happening? Oh, there's some problem with this. Okay, it's kn here. This kn is a Hilbert space. It is a Hilbert space where this inner product is defined by what's inner product of any two tuples. It is summation I runs from 1 to n xi yi conjugate, where this x it's equal to xi, I runs from 1 to n, and y equal to yi, I runs from 1 to n. They are in kn, okay. So now then we have this. Then what's the norm of x here? Norm of x, you can see that's equal to summation norm 2, that's called norm 2, I runs from 1 to n. You can easily verify it. mod of xi square whole power 1 by 2. So therefore norm of f of x, norm 2, this is equal to what's this key, this is x u1 x u2 x un norm 2. And that's by definition this summation. These are the entries. Its I runs from 1 to n mod of inner product x ui square whole power 1 by 2. And that you can see this is a, this ui is an orthonormal, is an orthonormal basis, so it's equal to, since this is equal to norm x2 actually, norm x2, because this set, because our x is here equal to, you can easily verify it is equal to summation I runs from 1 to n inner product x ui that you can easily verify it's equal to this. So that means the norm x2 square is equal to sum of this is, because this is true if and only, you can see this is true if and only if norm 2x is equal to square, it's square, okay, it's equal to summation. That's actually Bessel's inequality जो आपने की होगी, it's x ui square, okay. So this is true if and only if this, but this is true because this is ui is basis, okay, it is orthonormal basis of the Hilbert space H. So that means our x is equal to this by the previous theorem. That's the if and only criteria for orthonormal basis जो आपने previous theorem में किया है. So that means norm of fx2 is equal to norm x2. So therefore f is an isometry. It's an isometry. अब आपको चेक करना ये जो f it's also onto, ये onto भी है. So onto के लिए कोई भी वेक्टर लीजिए कि
then this element inner product x with u1 plus
so this element will so this is x with u1, okay, f of x is equal to, so inner product x with u1, so I cannot calculate this inner product actually, calculate this inner. So for x is equal to, x is a tuple here, x is an n tuple, then I want to find some element in H, so that image of that element, let's choose this here y, let's drop x, choose it y here. Okay, so y is the element, okay, y. So then y1, y2, yn, they are the, so then our y is equal to this tuple, n tuple, where these yi's, they are in the scalar field K. Okay, this y1, so this is equal to let's define x. Okay, so this is scalar. Okay, this is a scalar, so this is scalar. So can I define x in H so that y1 is equal to inner product of x with u1 and y2 is equal to inner product of x with u2. So for any x in H I can always find, but I want to do it the other way. So I want to find x in H so that y1 is equal to inner product of x with u1. So can I do it? This is a scalar, this is also a scalar, and this is also a scalar. Okay. This y1. So if I define map from suppose if it's one dimensional, उस केस में आपके पास तो यही है y इक्वल टू इनर प्रोडक्ट ऑफ x विद u1. तो उस केस में y को कैसे ऐसे एक्सप्रेस कर सकते हैं? अगर आप कोई एलिमेंट y लोगे, so can I find x such that inner product of x with u1 is equal to, inner product is a continuous function, that's right, inner product is a continuous function, inner product is a continuous function. तो इन्फिनाइट केस में इसने एक्चुअली इस थ्योरम का यूज़ किया है जो हमने कल के लेक्चर में की है शायद. Equal orthogonal basis if Fourier expansion for every x in H. Okay. This is and then so here. I want to construct an element from this. So it's a y in kn. Okay, y in kn. So whenever x is in H, I can write x as inner product x with u1 summation whenever you are phase orthogonal basis. And conversely, if I take an element that is square summable, so it's actually here. If x is Hilbert, then suppose this is finite. If x is this, then the idea of u. Okay, so let's define I think we define an element x. So define this, let me do it like this. Define x is equal to summation I runs from 1 to n yi ui in H. Okay, define this element. This is in H obviously because ui's are in H, so these y's are scalar, so this is in H, this element is in H. H is Hilbert space. Okay, then you can see that inner product of x with u1 is y1. Okay, actually I want this, so this is not clear. Now you can see this, then Let's find this inner product of x with u1. Okay, let's find this one. This is equal to inner product. This is a summation. I runs from 1 to n yi ui with u1, and since this ui is an orthonormal set, so at for I equal to 1 it will be y1 u1 y1 बाहर आ जाएगा, स्केलर है ये, so it is inner product of u1 that's equal to 1. But for the rest of the i's, inner product is 0, so you can see it's equal to 1. Okay, so in general you can see this. In general inner product of x with ui is equal to yi for all I runs from 1 to n. Okay, so this, therefore our x is equal to, therefore our x is equal to, therefore our x is equal to what? It is summation I runs from 1 to n inner product x with ui and ui. So this in h such that what's f of x? F of x is so by our definition this f of x, because x is equal to this, so f of x is this. F of x, what's the definition of f of x? It is जो आपने define किया है, what's happening here is, so it's inner product x with u1, that's the definition of fx, inner product x with u2, and inner product x with un. So that's it. But x with u1 it's y1 y2 so on yn. So that's so that's your y. Okay, so that means for each y in kn we can find x as fx equal to y. So therefore h is isometrically isomorphic to k, and it's also onto. So इसके अगर ये बेसिस, इसकी ऑर्थोनॉर्मल बेसिस अगर फाइनाइट होगी उस केस में ये it will be isometrically isomorphic to kn, where kn is endowed with that inner product जो हमने already discuss किया है. Now case second, if this set is denumerable, means countably infinite, if this is denumerable, if this set is denumerable, then what can we do in that case? In that case you can see that can define then if this is denumerable, okay, then you can see this summation and runs from 1 to infinity mod inner product x and un square. This thing is a finite, you can see this is finite thing. Okay, so therefore जो f of x होगा, which is by definition it's equal to inner product x with u1 inner product x with u2. This is in L2. Okay, ये L2 में होगा, square sum में होगा because of this. also it's L2 norm ये किसके बराबर होगा? So that's L2 norm of this infinite tuple. And this is obviously by definition it's this x un square and runs from 1 to infinity whole power 1 over 2, and that's nothing but it's a norm x, it's norm x. तो वहाँ पर शायद मैंने I think here it's not norm 2 here on this side. Okay, it's just norm x. Okay, because x is in Hilbert space. Okay, so this is norm x. इट्स एन एज, सो इसकी जो इमेज होगी वो उसके पास L2 नॉर्म है, इमेज लाइक हियर। तो ये जो इमेज है ना fx, इस पर 2 नॉर्म हुआ, L2 का नॉर्म। And this is equal to norm x. Why? Because our x is equal to this. Because x equal to summation, ये हमने ऑलरेडी किया है रिजल्ट, समेशन x u n square u, sorry, it's not like this. So this is what's x is summation and runs from 1 to infinity inner product of x with u and ये इसके बराबर, and this one, this is from Bessel's inequality and this is equal to, और ये इसके बराबर होता है if and only if norm of x is equal to this summation I runs from 1 to infinity whole square. Okay, this is norm square. ये तो है इसके बराबर, बट दिस इज इक्वल टू दिस इफ एंड ऑनली इफ दिस, वही हमने यहाँ पर अप्लाई किया है। अगर आप इसको देखोगे यहाँ पर हमने ये नॉर्म x के बराबर है। सो देयरफॉर f इज अगेन एन आइसोमेट्री फ्रॉम h to L2. Okay, so therefore f from h to L2 is an isometry. ये isometry है। Now we prove it's onto. Now this f is also onto. Linear तो है ये, is onto. Linear is simple. It's onto. So for this we choose any element y in L2. Let's choose this y, which is equal to say scalars में k1 k2 है, suppose infinite. It's in L2. So this means summation mod of k and square and runs from 1 to infinity is the finite thing. So again you can apply that result. So this gives अगर आप वो रिजल्ट अप्लाई करोगे जो हमने ऑलरेडी किया है, अगर इस तरह से है आपका जो दैट्स एक्चुअली द रीज-फिशर थ्योरम. So then this implies this thing summation and runs from 1 to infinity k and actually previous part में भी हमने रीज-फिशर थ्योरम का यूज किया, but it's finite version, that's very simple. So this is in H. Okay, this is in H. This belongs to H. ये H का नंबर है. Okay, and this so this is in H. So let's write this as x. So suppose this is x, and let x equal to this. Let's define this by x. Summation n runs from 1 to infinity k n u n. Then what's f of x? By definition, it is the inner product. This pen is not working properly. This is the let's do it. Inner product x with u1, inner product x with u2, so on and so forth. But you can see this inner product x with u1 as in the finite case it's equal to k1, and this is equal to k2, so on and so forth. That's equal to y. So that means therefore f is onto. Therefore f is onto, and thus in that case h is isometrically isomorphic to L2. So that means 1 implies 2. Okay, 1 implies 2. So this was the difficult part of it. Now the second implies third. That's very simple because we know that kn is separable. So second implies third. So we know that's very simple. ये हमने ऑलरेडी किया है ना फाइनाइट डायमेंशनल केसेस में. We know that K and the finite dimensional space is separable and also L2 is separable. ये भी हमने दोनों चीजें की है. is separable and they are also and separable Hilbert spaces. Okay, they are separable Hilbert spaces. So this is simple. Okay? Now third implies 1. Third implies 1. So let H be separable Hilbert space. Okay, let H be a separable Hilbert space. आपको प्रूव करना है कि H has countable bases. Separable Hilbert space. Okay, H be separable Hilbert space. So it has a countable dense subset. So let's take its countable dense subset. Let